So this is section 10.5, density and molar mass of a gas. So we've looked at the ideal gas equation, PV equals nRT, and now we're going to look at rearranging it a little bit and solving for things like density and molar mass of a gas. We know that we can find moles by taking mass divided by its molar mass. Mass being in grams, molar mass being in grams per mole, or the number that you find by adding them up on the periodic table, the upper right-hand corner numbers. I'll symbolize mass with a little m and molar mass with a capital MM, or just a capital M. We're going to take this mass divided by molar mass and we're going to substitute it in for N right here in PV equals nRT. Substituting mass and divided by molar mass in gives us the equation PV equals mass divided by molar mass times RT, or PV mmrt. PV equals MRT, PV mmrt. All right. Now we're going to take and use this equation several times in different problems, but we can rearrange it further knowing something way back from chapter 1, that density is equal to mass divided by volume. And we have mass and volume in this equation. And so we're going to rearrange this equation so we have mass divided by volume all in the same place. So here's PV equals M divided by MRT. PV equals MRT divided by M right here. Now I'm going to take and multiply both sides by M because I want to get rid of this M right here. So the M's will cancel. M will end up over here. And then I'm going to take and I'm going to divide both sides by V. So dividing by V right here means I have to divide by V this side, and my V's cancel. And then I'm going to divide both sides by RT. Divide both sides by RT right here. That means I have to divide this side by RT. So what's left on this side is mass divided by volume. Hey, that's what I'm looking for. And then on this side, I have molar mass times pressure divided by RT. And so my mass divided by volume, just taking it and putting it on this side of the equation, is equal to MP divided by RT. Mass divided by volume is known as density. And so density is equal to military police over rapid transit. MP divided by RT. Mass divided by volume. Let's do one equation or one problem that uses this density equation. Let's go to the next page in the textbook right here, and let's look at practice exercise 2 on page number 453 of your textbook. All right. I'm going to put practice exercise 2 right here, and it tells me right here that the mean molar mass of the atmosphere, molar mass of the surface of Titan, Saturn's largest moon, is 28.6 grams per mole. And it says the surface temperature is 95 K. So notice how I'm organizing my data here just like I did with the other problems. And the pressure is 1.6 atmospheres, or ATMs. Assuming ideal behavior, calculate the density of Titan's atmosphere. Well, we know that density of a gas is equal to military police over rapid transit, or MP divided by RT. We're given the molar mass right here. We're given the temperature right here in Kelvin. We're given the pressure right here in atmospheres. Now we need to pick an R that's in atmospheres. So make sure that you pick the correct universal gas constant to use to make sure that you have the right units to make the relationship work. Just looking for my universal gas constants here so that I can hold those up for you. And here we go for the different values that are available that hopefully you have in your notes. Maybe you want to pause and take a picture of this because you end up using those a lot. Okay, so M 28.6 grams per mole times pressure, and our pressure is 1.6 atmospheres, divided by R, and the R I have to use is the one in atmospheres, so I'll use this one right here, 0.08206 liters times atmospheres per mole times Kelvin. And then my last piece is my temperature, and my temperature has to be in Kelvin, which is 95 Kelvin. It's already there. The kelvins cancel with the kelvins, the atmospheres with the atmospheres, the moles with the moles. I'm messing with the units of grams per liter, which are units of density because that's a mass per unit volume. Let's put these values into our calculator. So 28.6 times 1.6, enter, divided by 0.08206, enter, divided by 95. And we end up with a density of 5.8, round 7, that's grams per liter for the density of Titan's atmosphere. Good luck with your density gas law equations.